Okay, in the last video, we already learned how to fill in the FMEA table, and finally from the FMEA, we have shortlisted a few parameters or key process input that we need to further consider. Okay, so in this example, we can use either Pareto concept or top quartile in order to select the variable to be uh, further investigate in the analyze phase. Okay, so based on the previous video, so we have selected spindle speed, depth of cut, and feed rate for the milling process, and also coolant temperature for the turning process to be further investigate in the analyze phase. And before that, we also need to conduct some data collection for us to have the baseline data. And basically, what type of data that we need to collect? Okay, so this to determine the type of data. So we need to look back at our cause and effect matrix. So from cause and effect matrix here, there are a few outputs that we already determined earlier. Okay, so right. So for us to collect the data, so we look at the highest total of the output score. Okay, so from the glossiness until the dent, so this is the highest output score, which is the roughness or the surface roughness. It means that in the further analysis, our output variable will be the surface roughness. Okay. In a real project, it's not necessary for us to limit the output parameters to only one. So we can choose maybe top three parameters, okay, from our cause and effect matrix here. Okay. Then we conduct or we collect the data for the existing process as our baseline data. So this is an example of the data that has been collected, okay, in I believe in the micron unit for the surface roughness. Okay, so the number of data here is depend on our problem. Okay, for actually the higher number of data is basically better for our analysis. Right, so next, once we already have our baseline data, so you will need to do some statistical measurement for the data. So we need to conduct the normality test to make sure that the data is normally distributed. Okay, so in Six Sigma, the prior requirement before we can conduct any other test is we need to make sure that the data is normally distributed. Okay, so we conduct the normality test. Okay, in this example, we can use Minitab software. For example, in this one is Minitab software, and we can conduct the normality test. Okay, so from the normality test, our p-value, okay, p-value is 0.118, okay, whereby the alpha value is 0.05. Okay, so since p-value that we obtain is larger than the alpha, the confidence level that we set, so we can conclude that the data is normally distributed. Okay, so this is the Anderson-Darling normality test. So we can obtain p-value 0.118. So this one is larger than the alpha, and again we can accept the assumption that the data is normally distributed. Okay. Then as an addition to normality test, we also can plot the data into a run chart, okay, to see if there is any pattern that we can observe from the data. So based on the plot that we made, so roughly the data is roughly balanced between the upper side and the lower side, and the data is also roughly or randomly distributed, okay, among the upper and the lower side. So means that the data is, we can say that the data is randomly samples or randomly taken or randomly distributed. Okay. Then we also can conduct the process capability in order to know our current process capability. Right, so this is one of the tests that we can conduct on the process capability. Okay, so from here basically we can get the Z bench and also CPK for the process. Okay, so we need to refer to the standard value. Okay, what does the certain CPK here means? So basically, if CPK 0.022, it's definitely shows that the process are incapable. Okay. All right. So next one, we already established the baseline data. So we already know our current process capability. So next we can proceed with the analyze phase. Okay. So the purpose of analyze phase is to prove the hypothesis that we made from the measure phase, from the earlier phase. So we have identified 4 variables or 4 parameters that we think contributed to the surface roughness. But that one is basically based on our assumption. So in analyze phase, we are going to test or to validate our hypothesis, okay, using the actual data. So in the analyze phase, we need to set a hypothesis. So since we have 4 variables earlier, so at least we need to have 4 hypotheses. So the first hypothesis is on the first variable. So we state that for null hypothesis, there is no relationship between spindle speed and surface roughness. And the alternative hypothesis, we state that there is a relationship between spindle speed and surface roughness. So just the same for hypothesis 2 until 4. So we claim that for null hypothesis, we claim that our variable is having no relationship with the output one. Okay, so there is no relationship between depth of cut and surface roughness. Okay, so this is the hypothesis. Then number 3 is about the feed rate of the milling and surface roughness. So for the null hypothesis, we claim that there is no relationship between feed rate and surface roughness. Hypothesis 4, we said there is no relationship between cooling temperature or coolant temperature of a process and surface roughness. So these are the hypotheses that we set. Okay. So in order to accept or reject the null hypothesis, we must conduct an appropriate hypothesis testing, and we look at the p-value as well as the f value in the statistical test output. Right, so in order to conduct the hypothesis testing, again, we need to do the data collection if we still didn't have the data. Okay, right, so in this example, since we have four hypotheses, so we need to have at least 4 set of data which represent the different input variables that we think contributed to the output variable, which is the surface roughness. So for speed, for example, okay, so we collect the data with different speed. Okay, this this is 750 rpm, 1000 rpm, and 1250 rpm, and then we collect the surface roughness data. Okay, so this is in a slightly different unit, I think. So previously is in micron, so this is maybe in 10 power of minus 8. Okay, so this is just the unit that we use. Okay, then for feed rate, we also collect three types of, or three categories of data by using 150, 300, and 450. For temperature, we collect the data of 24 degrees C and 30 degrees C, and for depth of cut, we collect 0.25 and 0.75 mm data. Okay, then we conduct an appropriate hypothesis testing. Okay, so for spindle speed and feed rate, since we have three groups of data, so we normally utilize the ANOVA test. Okay, then for for depth of cut and coolant temperature, we have two groups of data, so we utilize two sample t-test. So we conduct the t-test and also ANOVA, and we are looking for the p-value from the statistical test here, and then we compare our p-value with the alpha. So the confidence level is for this test is at 95%, so the alpha is 0.05. Okay, so whenever p-value is smaller than alpha, so we reject null hypothesis. Okay, so when p-value is smaller than alpha, our alpha is 0.05, so we reject the null hypothesis. Okay, which means that for the first factor, okay, our null hypothesis earlier is there is no relationship between spindle speed of milling and the surface roughness. But since based on the data that we obtain and the statistical test, so we reject the null hypothesis, means that we accept the alternative hypothesis, okay, which is there is a relationship between spindle speed and surface roughness. So now based on the data and tests that we conducted, now it was proven that there is a relationship, okay, between spindle speed and the roughness, surface roughness. Okay, the same thing is also for feed rate. Okay, so we reject null hypothesis. So as a summary, we can say that feed rate has a significant effect on the surface roughness, or we also can say that feed rate has a relationship, okay, with the surface roughness. For depth of cut, also we reject null hypothesis, but for coolant temperature, we get p-value 0.927. Okay, so in this case, since p-value is larger than alpha, so we accept null hypothesis. So for this parameter, the coolant temperature doesn't have significant effect on surface roughness. Okay, so we accept the null hypothesis for hypothesis number 4. Okay, no relationship between coolant temperature and surface roughness. Okay, so now we only the remain parameters is only spindle speed, feed rate, and depth of cut. Alright, so basically when we already got the summary, either to accept or reject the null hypothesis, basically we already concluded the analyze phase. So basically we have ended that phase. So next we move to the improve phase. Okay, so the purpose of improve phase is to improve the process by reducing the variance. Okay, the process variance. We try to reduce the process variance. Okay, so for this purpose, we can use any suitable design of experiment approach. Okay, for example, we can use full factorial design, fractional factorial, we can use Taguchi, we can use response surface method, okay, in order to improve the process. So basically in this phase, it's involved the design of experiment or conducting the experiment. Okay, so from our hypothesis testing earlier, so there are three variables that was proven have the relationship or have the effect on the surface roughness, which are spindle speed, feed rate, and depth of cut. Okay, so now we will conduct an experiment. Okay, let's say we choose to test at 3 level, okay, for each of the factors here. Okay, so level to be tested, these are level to be tested for each of the input variables. Okay, so for design of experiment, as I mentioned, we can use any suitable type of DOE. Okay, for example, in this one, we utilize Taguchi design. Okay, so we utilize Taguchi design with L9 orthogonal array. Okay, so this is the table of the experiment. So it's set 1 here means the low level, 2 is a medium level, and 3 is the high level. Okay, based on our level here. Okay, this is 1, okay, low level. This is 2, medium level, and this is 3, high level. Okay, so this is the table. This table is basically automatically generated okay, in the software, in the Taguchi, in the Minitab software. Okay, we also can utilize other DOE software. Okay, for example, the Design Expert or the free or the open source software. Okay, we also can use SPSS. Even I think there is the website that offering the online design of experiment table as well. Okay, right. So for this one, so we conduct an experiment, means that we set our process to according to this level. So means that for the first factor, second factor, and the third factor. So number one, experiment number one, we set all the factors at low level, and then we conduct our experiment and measure the output. Okay, in this case, is the surface roughness. Okay, then number two, we set the first parameter at level 1, second parameter and third parameter at level 2, and then again we conduct the experiment and measure the output. Okay, so we conduct the full experiment here, okay, following the Taguchi table. Okay, then we analyze the result. Okay, based on the analysis of Taguchi design, so this is the main effect plot for mean and main effect plot for signal to noise ratio. Okay, so this is only for the Taguchi design. If we utilize other different approach, so we may not get the SN ratio main effect plot. Okay, so but for other approach also we will get the main effect plot, okay, for the means. Okay, so okay, so this is basically the problem that we want to minimize, means that we want to obtain the minimum surface roughness. So for main effect plots for mean, so we are looking for the low level. So it means that the based on the observation from this graph, so basically we can say that the optimum level for the process, okay, for parameter A is at level 1. Okay, for parameter B is roughly just the same between 1 and 3. So maybe we need to look in detail later. And for C is also just roughly the same, but we can see that level 3 is slightly better compared to level 2, level 1 and level 2. So this is what we can see. And another thing is based on this plot also, we can say that the first parameter, okay, which is the spindle speed, it gives the largest effect because the gap between low level and the high level is the most what we call the most significant gap that we get, okay, compare with B, for example, between the top value and the lowest value is slightly smaller than this one. And for C is not really significant, I think, because the difference between the maximum and minimum value are too small. Okay. Right, so based on the Taguchi analysis, the optimum result is for spindle speed is 1, for feed rate is 3, for depth of cut is 3. So as I mentioned, for example, if we're not sure, for example, for parameter B, which one is better, either at level 1 or level 3, so we can look at the output here. Okay, response table for the mean. So we can see that for level A, okay, so level A, this one is obviously the best one, the minimum one, compare with level 2, 2 point something, and level 3, 2 point something. So level 1 is the best. Okay, so for B, this is the smallest one. Okay, although is roughly just the same with level 1. So level 3 is 1.84. This level 1 is 1.88. So this one is roughly slightly better than level 1. So level 3 is slightly better than level 1. So C also is almost the same, but again, level 3 is slightly better than level 1 and level 2. So from there, basically, we can say that this is the optimum parameters that contributed to minimum surface roughness for our process. Okay. Then on top of that, we also can generate mathematical model in the Minitab by using regression analysis. Okay, so the regression equation is this one. So we can generate the regression equation, which basically can represent or can be used to predict the surface roughness when we plug in a different parameters value. Okay. But if we look at this model, okay, this is the first order model, means that this is a linear model. So if we look at the R square value, okay, R square value is only 61%. Okay, so it means that the data is not really, or the equation that being generated here is not really representing the whole data. Okay, maybe only around 60% of the data are located on the regression line here. Okay, so means that the model here is not really accurate. Okay, okay, so when we obtain the value lower than maybe 75%, so normally we need to do something in order to improve the accuracy of the model. So in this example, so we try to test for the second order model. Okay, previously we only consider A, B, and C. So now we try to test for the second order. Means that we try to investigate the interaction between A and B, B and C, and A and C. So we try to calculate the output from the multiplication here. So A times B, so we multiply A value and B value, so we'll get this one. Okay, for example, here 3 and 3, so 3 times 3 is 9. Okay, so just the same for A and C and B and C. Okay, so we try to include this interaction in our model. So again, when we get this one, just utilizing the same output that we obtained earlier for RA. RA is basically just the same with the one that we collect earlier. Okay. So we just rerun back the regression model. Okay, but now we are considering the second order model. Okay, so this is the new model. Okay, so if we look at the model, they have A and B interaction, A and C, and also B and C. And if we look at the R square value, So the value has tremendously increased to 96%. So means that roughly 96% of the data are located on this model. So if we plot the line for this model, so basically around 96% of the data are located at the plotted line. So which means that our second order model here is really good. Okay, so this can be utilized to predict the surface roughness. Okay, so now we can predict our surface roughness by plug in the input variables in the formula here. Okay, so we can use, for example, we have a certain target. We want RA to be, for example, 100. So we try to find a combination of A, B, and C so that we can get the RA as we require. Okay, so this is the mathematical model. Okay, so that and the improve phase. So suppose from this phase we should be able to obtain the optimum parameters value. Okay, and that one should improve our process variance. Okay, so now we move to the final stage, which is the control phase. Okay, the control phase, so we run the operation using the optimum parameter setting. So now we can run our process, our service and so on using the optimum parameter setting, and then we monitor the process. So this is the control phase. Okay, so means that when we want to run this one, so we utilize this optimum level setting for the input parameters for all of the process that we run. Okay, and then we monitor the process. So for that purpose, we can utilize the control chart, okay, to measure or to observe the output. Okay, so we try to identify if there is any pattern that we can observe or any non-random factor or non-random observation that we can get from the control chart here. Okay, so we continuously control the process. Okay, then if we find any what we call non-random pattern and so on, so we need to further investigate the causes and so on. Okay, so up to this level, normally if the data is within the limit that we required and the variance is also has been improved, so we can conclude that our project has succeeded. Okay, then the process is not stopping there, so we need to reinvestigate other factor as well, and also reinvestigate other causes and so on. So the Six Sigma will supposed to be conducted continuously for our process. Okay, so that's all. Thank you.